All right, welcome back. So in the last video, we were just talking about the old brass tacks and sort of the structure of the assignments of this class. Now, let's get back into some familiar, hopefully, vocab that we'll be using a lot in this class. And if this is totally new to you, that's totally fine. But this should at least be somewhat familiar to you if you've ever taken a stats class or if you're familiar with any kind of scientific writing. This language is used a lot. So let's just get into it. So we study statistics, or we are currently studying statistics. But what is that? Well, what statistics is the process of collecting some kind of sample and making inference about the population, the whole thing. We're trying to paint a big picture here, and we're just doing each brushstroke based on the sample that we have. Okay, and so a statistic, singular, is just something we use to describe the data. Okay, the data that we have, the data that we collected, and that looks like tons and tons of things. Okay, but traditionally we just have a few that we use, at least for this class, and for other classes too. And as you get into more advanced classes in statistics and econ and math or wherever, these statistics, these individual statistics, can become a little bit more complicated. But for now, we kind of stick to these sort of 5 things here: the 3 M's and then 2 standard blanks. Okay, and so already you probably know where this is going. The most frequent statistic that we use in this class and in a lot of classes and in research and publications and all this is the mean. Okay, and that's also known, there we go. That's also known as sort of the expected value of something. Okay, so you calculate the mean of some sample, and if you were to go out and go collect a similar sample, well, you can expect the mean of that data to be similar to the mean of the data that you just collected, right? Okay, so no biggie. This is also known as an average, kind of more colloquially. Of course, all 3 of these M's that we're going to get to are also known as averages, but most of the time people just mean mean as the average. Okay, so that's the expected value. That's kind of the traditional average we're used to hearing. What about these other 2? Well, we also have what's known as a median. Okay, and the median is just what marks the 50% mark. Okay, or kind of the halfway point in our data. So that just means that 50% of our data is below that value and 50% is above that value. Okay, that's also frequently used. We won't be using it too much in this class, but it is important to know at least sort of the definition there. And the last M here is the mode. The mode. So what is the mode? It's honestly probably my favorite statistic because it represents the most frequently observed value. Okay. Now in continuous data, which we'll get to in a second, data that has an infinitely small degree between, let's say 1 and 2, and 1 and infinity, right? The mode becomes kind of difficult to describe, but when you have countable things, so like 1, 2, 3, 4, 5, these discrete numbers, the mode is a little bit more easy to calculate, right? So these are all legitimately calculated. These are all legitimate to use in statistics, but we are more focused on the mean really than anything else, at least between these 3 here. Okay. Now we have these 2 standard blank. What does that represent? Well, if you've taken my class for 2050, you've probably seen both of these. If you've taken it somewhere else, you may have only ever seen the first one here, standard deviation. Standard deviation. And we'll actually get to the definition of that here in a second. And the last thing here, the most frequently used statistic we'll be using in this class. Nope. Standard error. Standard error. Again, definition inbound in just a second. But these are the most frequently used statistics in this class, and often in other research positions too. So let's just move on to some definitions of these last two things here, because these two things people get confused quite often, and that's okay. So standard deviation versus standard error. What the heck? Okay, well, let me just tell you now, standard deviation is 100% all the time, always about the data that we have, okay? So we have somewhat tangible data, okay? We went out and collected a sample of 100 or whatever, and that sample is going to have some mean, it's going to have some median, it's going to have some mode, maybe, but it also is going to have some deviation to it, okay? So each point is not always right at the mean, right? We know that data has a bit of a shape to it, and we use standard deviation to quantify that shape, okay? And we can kind of see that here in this figure, right? So what standard deviation is, at least kind of casually, is how far the data on average deviate from the mean. So for instance, if we were to go out and calculate, or sorry, if we were to go out and sample, let's say 100 college-aged males and got their height, we found a mean of 5'8". Okay, whatever. That's just the mean. How do we know the shape? How do we know the overall deviation on average of that data that we have? Well, let's say that we then calculate a standard deviation of 2 inches. Okay, so that means that on average, each person in that sample deviates 2 inches away from the mean. Okay, now that is not to say that the smallest value we saw was 5'6" and the largest value we saw was 5'10", but it is to say that the most frequent occurrence of heights is between those two values that I just said. We still did see smaller values than 5'8", or I guess 5'6" and 5'10", but they just occurred less frequently. Okay. Now, we might just say that maybe this green line here kind of represents the shape, and we will pretend that these are not from -5 to 5, but maybe 5'8" here in the middle, and then this -1 would be replaced with 5'6", and +1 with 5'10", right? We still do have data out here in the tails, they just don't occur as frequently as the stuff here between 5'6" and 5'10", okay, with a standard deviation of 2 inches. Now, if we were to go out and calculate a similar thing, but we found a mean of 5'10", for instance, with a standard deviation of maybe ½ inch, okay? Again, just totally new example, not related to the last. Well, then our data would look something like this. We have more data occurring here at the mean, where then we had a smaller standard deviation. We have a narrower distribution of our data that we have. Okay, and now it might not always be perfectly symmetric like this, but you know, this is just an example. And then on the other hand, we have a larger standard deviation. It's going to be more flat, right? So we have almost equally occurring heights the further we go out, right? And that's pretty much just that, right? So standard deviation is 100% oriented around the data that we have. Okay. We're not making any inference about anything. It just is what it is. And that's that. Okay. Now, going back kind of to the definition of what we do in statistics, we take a sample from some population and we try to relate whatever we can back to the population. Okay. So we make inference based on what we found here in the sample to the population. Okay. However, we know that we're going to be slightly wrong here. We're not always going to be on the money all the time. So for instance, we go out and calculate some mean. We'll just say it's 5'8", again, similar example, for college-aged men with some standard deviation, okay? But we know that that's not the whole picture, okay? It might be close to the whole picture, but it's not going to be exactly on the money, okay? We're going to have some level of inaccuracy there, or uncertainty, we'll say. So we can calculate what's called a standard error of the statistic that we calculated, okay? Now, these two things are related in that you need standard deviation to calculate standard error. You also need sample size, depending on, what standard error you're calculating. The formula looks a little different for each statistic, but we're not going to worry about it for now because the computer does all the work, which is great. We don't have to do any pen and paper math, which is wonderful, I think. Anyway, so in this case, we'll have some standard error associated with the mean, okay? Because we don't have the whole picture. But if we were to make this little cookie cutter cut a little bit larger, okay, we're going to get closer to the overall population. That means our standard error of whatever statistic we calculated will be slightly smaller. And the bigger sample we get, the closer we get to this whole population here, the smaller the standard error is, which means that we are more certain of the statistic, or at least relating it back to the population, okay? And of course, if we were to somehow get the whole population, if we were to cut out this whole population, the standard error would be super, super small because we just got nearly right on the money, okay? Now, that almost never happens because populations are kind of always changing, or we might not have a good idea of what the whole population exactly is. Oftentimes it's kind of an abstract idea, but also the population could be known, but it's just too expensive to get everybody in the population. And that is kind of related back to the census. The census, at least in the US, is a big undertaking. It takes forever to get kind of an idea of all the people that live in the US. We get all sorts of measurements about them, not so much height, but like income, demographics, that kind of thing, right? But even the census, it attempts to get the whole population, but it doesn't, right? It always leaves people out, which is unfortunate. So we use statistics from the census to calculate just to get back up to the population, right? And so that's pretty much that. So standard deviation, just as a recap, is of the data. So we have the sample and we have some standard deviation associated with the data. Standard error is for whatever statistic we calculated from the data and how close it is to the population. The bigger cookie cutter we make from this population little cookie here, then the smaller the standard error is. The less that we incorporate from the population, the larger the standard error is going to be. And this goes for pretty much any statistic, okay? Mean, median, mode, when we get into regression, slope coefficients, that kind of stuff. But for now, we'll just keep it in general, standard error of a statistic, how accurate the statistic is, okay? So that brings us then to variable types. And this is where we're going to get back into some, hopefully some familiar kind of lingo. Again, if it's not familiar, no biggie. I don't mind at all. So variable types. Oftentimes we see X or XI that is some kind of, and you have a bunch of different people calling it different things, but in this class, we're going to be calling it a predictor variable. And when we get into regression, this will be a little bit more clear. I think it makes more sense in regression than anywhere else. But it's also known as the independent variable. And this language, you can stretch either of these as far as you want, but we'll just keep it to these two things for right now. Now, you can always have more than one. In regression, those are known as predictor variables. We're not going to get straight into regression. We're going to do t-tests first. And that might be, hopefully that's familiar from intro stats, especially if you took it with me. But the nice thing about these predictor variables is that they can be either, here we go, numeric, so numbers, right? 1, 2, 3, 4, or 1.1, 1.2, 1.3, et cetera, and they can be categorical, okay? So male, female, freshman, sophomore, junior, senior, that kind of thing, right? So in this instance, the categorical instance, if we were to say, how do the heights differ between males and females? Well, our predictor variable is males and females. It's sex there, and that's categorical, okay? M and F, easy as that, okay? But if we wanted to say, how does height affect weight? Well, then that's numeric. Our predictor variable is height, and that's numeric, okay? So 5'7", 5'8", et cetera, et cetera. I suppose in that instance, it might be a little easier to use inches instead of feet and inches, but you kind of see where I'm getting at there. And I've hinted on it so far, but why is our outcome variable? It's the thing that we want to see a difference. Okay, that's the thing that we're testing essentially. Now I'm going to hint at it, or I guess just say it again. But in this case, the categorical case, if we wanted to test the difference between males and females and their height, our predictor variable is categorical males and females. And our outcome variable, our dependent variable, is height in that case. Okay. But again, if you wanted to say, well, how does height affect weight? Well, our predictor variable is height. It's numeric. And our outcome variable is the thing that we're trying to measure, and that is weight in this case. The nice thing about weight, no, not weight. The nice thing about this, in this class at least, is that it's always going to be numeric. There are classes and statistical methods that you can use, take and use to, determine the outcome of an event happening. So a 0 or a 1, or a yes or a no, or more classification kind of examples. But for this class, boy oh boy, we're just going to stick with numbers for the outcome, because it's just going to take too long to go over anything else. So traditionally, the independent variable causes an effect on the dependent variable, or the predictor variable predicts the outcome, and that's pretty much that. For this class, I absolutely hate independent and dependent, because to be totally honest, I get it confused all the time. So we're going to stick with predictor and outcome. I think that's just the easiest here. Now, a couple examples down here. You can read it yourself. How long you sleep, predictor variable, and it's numeric. So 8 hours, 7 hours affects your test score for whatever test. That outcome variable is numeric, right? You get an 80, 85, 82, 90, whatever. Okay. Or, actually, before I go on, in this case, this is a regression, right? We draw a line. Again, this is, only a hint of what we're doing. You don't have to know this right now. But this is more of a regression question. And then the second kind of example here, how sex, which is our predictor variable, and it's categorical, it's male and female, affects height. Okay. And that's the outcome, and that's numeric. Easy enough. And in this case, this would be a little t-test. Okay. Again, no big deal if you don't recall that, but good on you if you kind of figured it out. Now, oh man, this numeric, well, actually, categorical is easy. It is usually 2 or more things that I mentioned before: male, female, freshman, sophomore, junior, senior, etc., grad student, whatever. That's pretty easy. Okay. This numeric, though, these can be a little different. Okay, and that's okay. So we move on to the type of numeric variables we can have. The first one is continuous. It's probably the most, well, it's out there. It's not too difficult, but it is, you can get a little finicky with these things. Okay, so it's numeric variables that have an infinite number of values between any 2 values. Okay, so what the heck do I mean by that? Well, how many numbers are in between 1 and 2? Whoa, a ton, right? All of them. 1.1, 1.11, 1.1111, etc., right? The infinity in there is very large. Okay, and that's what I mean by that. Okay, so I give this example here of all these all these hunks here, all these famous people and their heights. Okay, and so you have old Josh Hutcherson down here. He's 5'5", right? Next guy, old Dave, is 5'6", but we know that there's a bunch of values in between there. Okay, there's a bunch of heights that you can be. And the example here is old Jamie here is 5'10". Michael B. Jordan is also 5'10", but if we were to zoom in, there's going to be a slight difference between those two. Okay, and then here I am, 5'11". Wait a second. Oh no, that's Michael Fassbender. Sorry, I get us confused all the time. Anyway, that's me, or that's Mike. And there is some distance between 5'10 and 5'11, right? But we know that there's a bunch of in between there too, okay? And we go on, right? These typically, this is the easiest, I think, to kind of wrap your head around. Height, weight, age, time, et cetera, et cetera. Time gets a little funky. We're not going to be doing too much work with time in this class because there's a whole class oriented around time series. But for now, this is the type of at least the most frequent use of continuous variables that we'll see. Okay, the next one is discrete. Discrete numeric variables, and that just means that they're countable. Okay, so 1, 2, 3, 4, 5. We're just kind of binning things. We're kind of putting things into boxes. Okay, sometimes it's rounded. Sometimes it's done by the decimal. So 1, 1.5, 2, 2.5, that kind of thing. There's even spacing between each possible value. Okay, this tends to be it's used frequently. Oftentimes it's used out of convenience. Sometimes it's helpful, sometimes it's not. You know, whatever. It's not that big of a deal. We don't treat them any differently in R, but it is good to know the difference between the two, right? So some examples here: number of people in a class, 30, 31. You can't have any half of people, right? Number of correct answers on a test. You got 100 correct answers. You got 99. I guess suppose in this case, you can't have half correct answers, right? And either is or isn't. Number of home runs, you kind of see where I'm getting here, right? It's all countable. Theoretically, if you had enough time, you could count up to really, really large numbers, right? But you can't sit down and count numbers in between numbers, right? So whatever, no biggie, right? This is it. We have discrete and we have continuous. And then categorical, it's the easiest, I think, at least to wrap your head around. It's just a finite number of categories or distinct groups of things, right? So male, female, education level, I use that a lot. Age group, so that's a little different. So you'll see like 10 to 12, 13 to 14, or I guess 13 to 15, whatever, 21 to 25. We use bins, right? We kind of throw everybody who meets that criteria into one group, and that's easy enough, right? Sometimes, at least with the age group, categorical variables can be broken down, and you can get back to continuous or at least to discrete. But sometimes out of convenience, it's easier just to put people into bins like that, or at least in this case, yeah. Education level, same thing, right? Whether you like pepperoni or whether you like pineapple on pizza or whether you are a sane person. Okay, I think this is an abomination, but whatever, like you can do whatever you want. Last kind of note here, categorical variables can be two things. They can be ordinal or they can be nominal. Ordinal just means that there's a time component to it, or at least an order to it. So the easiest, I think, example here is education level. So freshman is first, and then sophomore is all of the stuff you did as a freshman plus some other stuff. And then junior is all of the stuff you did as a freshman, sophomore, and some other stuff, et cetera, right? Whereas nominal is there is no order to it. You either are or aren't. So sex, I think, is the easiest kind of thing there. There's no order there. It either you are a male or female, right? So that's pretty much that. Again, just some basic examples. I know that you can get, very, very detail oriented with a lot of these things. But for now, we're just going to use that as the example. So with that, I believe that's it. So I will catch you in the next video. All right.